Picture the tiny battery inside a wristwatch. It is smaller than a coin, and most people forget it even exists until the watch stops ticking one day. Now imagine a battery that same size, but instead of dying in a year or two, it keeps working for 50 years straight. No charging cable, no plug, no swap. That sounds like a magic trick, and honestly, a lot of videos online will tell you scientists cannot explain how it works. That part is not true, and by the end of this video, you will actually understand exactly how this strange little device makes power, why it took decades to build, and why it still cannot run your phone, at least not yet. If stories like this get your brain buzzing with questions, sticking around and hitting subscribe means you will not miss the next one, because this channel digs into the real engineering behind China's biggest tech claims, not just the headlines. No pressure, just an open invitation if strange machines and real answers are your thing. Let's back up for a moment and think about what a battery actually does. Every battery you have ever used, from a phone to a flashlight, works by pushing tiny charged particles called electrons through a circuit to make electricity flow. Normal batteries do this using a chemical reaction, which is why they run out. The chemicals inside slowly get used up, kind of like a campfire burning through its wood, and once the fuel is gone, the fire dies. This new battery does not burn chemical fuel at all. It taps into something completely different. Something that has been quietly powering spacecraft since before your grandparents were born, and it never has to be plugged into a wall to top itself back up. For almost 70 years, engineers have known that radioactive material gives off a steady trickle of energy as it slowly breaks down. This is not new information, even if it sounds like something out of a comic book. Scientists built nuclear batteries for satellites and space probes back in the 1960s. NASA used them to power the Voyager spacecraft, and those probes are still sending signals from far outside our solar system today, decades after launch, long after any normal battery would have died and been forgotten. So if this idea is so old, why did it take until 2024 for a tiny nuclear battery to show up in a coin-sized package that regular companies could actually use? The answer is that old nuclear batteries were never small, safe, or cheap enough for daily life. The ones on Voyager use a material that gets extremely hot enough to boil water, and they are wrapped in heavy shielding to block dangerous radiation. That setup weighs several kilograms and costs millions of dollars, which is perfectly fine for a spacecraft with a budget the size of a small country's, but completely impractical for anything sitting in your pocket. You could never put that in a pacemaker inside someone's chest or a sensor stuck inside a bridge. Engineers needed a version that was small, cool to the touch, safe enough to hold in your hand, and cheap enough to manufacture in bulk. That combination seemed almost impossible for decades, which is exactly why this breakthrough turned heads when it finally happened. There was also a materials problem sitting underneath all of this, one that had almost nothing to do with the radioactive part and everything to do with what sat next to it. Even if you shrink the radioactive core down to a tiny size, you still need something next to it that can catch the energy being released without falling apart under the strain. Most materials used in electronics, like the silicon inside your laptop, slowly get damaged when radioactive particles hit them over and over, the same way sandpaper wears down a piece of wood a little more with every single pass. Engineers needed a material tough enough to survive decades of that kind of constant bombardment without cracking, warping, or losing its ability to conduct electricity properly. That search for the right material is really where this whole story picks up speed, and where China's research labs started pulling ahead of the pack. Think about a rooftop solar panel for a second, the kind you might see bolted to a neighbor's roof. Sunlight hits the panel, and the material inside catches that light and turns it into electricity you can actually use. A radioactive battery works on a surprisingly similar idea, except instead of catching sunlight, it catches tiny particles being thrown off by a decaying radioactive material. Picture a slow, gentle rain of energy particles falling constantly, day and night, whether it is cloudy or sunny outside, because this rain does not come from the sun at all. It comes from atoms breaking apart deep inside the battery itself, hour after hour, year after year, without ever needing a break. So what does this rain actually hit once it starts falling? Here is the step-by-step version, broken down piece by piece, so none of it feels like a mystery. Inside this battery sits a thin layer of a radioactive material called nickel-63. This is a special version of ordinary nickel, the same metal used in coins, except its atoms are unstable and slowly fall apart over time instead of sitting still forever. As they fall apart, they release small particles called electrons, kind of like tiny sparks flying out in every direction from a sparkler on the 4th of July. Except this sparkler never actually burns out. Right next to that layer sits a thin sheet of diamond, grown carefully in a lab rather than dug out of the ground like a jewel. This diamond is not for jewelry, and nobody is putting it on a ring. It acts like a super-sensitive catcher's mitt, grabbing those flying electrons before they escape and turning that motion into an electric current strong enough to power a circuit. Why diamond out of every material available to engineers on Earth? Diamond can handle a beating without breaking down, which matters enormously here. It resists radiation damage far better than the silicon used in your phone's battery or your laptop's chip, meaning that same sandpaper effect barely scratches its surface even after years and years of constant exposure. It also barely heats up, so the whole device stays cool and stable for years on end instead of slowly cooking itself from the inside. This matters because heat is often the enemy of small electronics, slowly wearing parts down the same way running a car engine too hot for too long shortens its life dramatically. A material that stays cool naturally solves a huge chunk of the durability problem before engineers even have to think about adding extra cooling systems. Layer several of these nickel and diamond sandwiches on top of each other, seal the whole thing inside a coin-sized casing, and you get a steady trickle of electricity that keeps flowing for as long as the nickel 63 keeps decaying, which happens to be a very, very long time. Each layer on its own only produces a whisper of power, barely enough to notice if you were holding it in your hand. But stack enough whispers together, and you start getting a signal strong enough to actually run something useful. The same way a single drop of rain does almost nothing to a dry field, but enough raindrops falling together over time can fill an entire reservoir to the brim. So what happens when engineers finally stack enough of these tiny layers together to make something powerful enough to matter in the real world? This part of the story is not a rumor floating around the internet, and it is not something pulled from a science fiction script. A company called Betavolt New Energy Technology, based in Beijing, announced this battery publicly in January 2024. They named it the BV100. It measures just 15 millimeters by 15 millimeters, smaller than a coin, and it produces about 100 microwatts of power at 3 volts. Betavolt stated the battery is rated to last around 50 years before its power drops to half strength, which lines up with the known half-life of nickel 63 as a radioactive material, a number that has been measured and confirmed by physicists long before this particular product ever existed on paper. Betavolt is not the only Chinese research group working on this technology either, which is worth pointing out clearly. Researchers connected to institutions including Northwest Normal University and teams within the Chinese Academy of Sciences have published papers on diamond-based betavoltaic cells, testing different layer designs to squeeze more power out of the same tiny footprint. Betavolt has said it is working toward a 1-watt version of this battery by 2025, which would be roughly 10,000 times more powerful than the BV100, though that larger version has not yet been independently confirmed by outside labs working separately from the company. That kind of jump would move this technology from powering tiny sensors to potentially powering small consumer devices, which is exactly the leap engineers around the world are racing toward next. The company has also stated the battery is safe to carry, does not catch fire or explode, and releases no external radiation, since nickel 63 mainly emits low-energy electrons that get fully absorbed inside the diamond layers themselves, similar to how a thick winter coat blocks a light breeze from ever touching your skin underneath it. This safety claim matters a lot, because the word nuclear tends to make people nervous immediately, and honestly, that reaction is understandable given history. But the type of radiation involved here is genuinely weak compared to what powers a nuclear reactor or a nuclear weapon, closer in strength to the natural background radiation you already get from ordinary sunlight or from eating a banana than anything resembling a real hazard to a human body. None of this exists purely on paper either, which is really the part that separates it from a lot of flashy tech announcements that never go anywhere. Betavolt has stated the BV100 is already being tested for use in medical devices, including pacemakers, where a battery that never needs surgery to replace could genuinely change how doctors treat heart patients for the rest of their lives. Right now, standard pacemaker batteries need to be surgically swapped out every 5 to 10 years, which means repeated operations, repeated risks, and repeated costs stacking up for patients over time. A battery rated for decades could mean 1 surgery instead of 5 or 6 over a patient's entire lifetime, sparing people years of anesthesia, recovery time, and the small but very real danger that comes with any surgery performed near the heart. The company has also mentioned testing in tiny sensors, drones, and equipment meant for extreme environments, like deep-sea exploration tools or devices operating in the freezing cold of outer space, places where changing a battery is either extremely expensive or flat-out physically impossible. Think about a sensor bolted to the outside of a satellite, orbiting hundreds of kilometers above the surface of Earth. There is no repair crew floating up there, no toolbox, no way to swap in a fresh battery when the old one finally dies out. A power source that simply keeps working for decades without anyone ever touching it turns an enormous logistical headache into a problem that quietly solves itself before it even starts. Other countries are not sitting still while this unfolds either, which is an important piece of context to keep in mind. Research teams in the United States, including groups connected to the University of Missouri, have worked on similar diamond-based nuclear battery designs using a different radioactive isotope entirely. City Labs, a company based in Florida, has sold small nuclear batteries called tritium Betavoltaics to industrial and military customers for over a decade already, though at a much higher price point and a lower power output than what Betavolt is now publicly claiming. Researchers in South Korea and parts of Europe have also published early studies exploring similar Betavoltaic designs, which means this is less like a single company's secret project and more like a shared global scientific race, with several serious runners lined up at the starting line. So this is not a one-country race happening quietly behind closed doors somewhere. It is a genuine global scramble to be the first to make nuclear power small, safe, and cheap enough for everyday machines that ordinary people actually use. Whoever solves the cost and manufacturing scale problem first will likely set the standard that the rest of the industry follows for years afterward, the same way early smartphone makers ended up shaping what every single phone released since has basically looked like. What happens to entire industries once someone actually wins that race outright? Zoom out for a second and think about what genuinely changes if this technology matures the way its supporters hope it will. Remote weather stations scattered across deserts or mountain ranges could run for half a century without a single maintenance visit from a technician, quietly logging temperature and wind data through decades of storms nobody ever has to trek out there and check on by hand. Ocean sensors tracking climate change could sit on the seafloor for decades, quietly gathering data long after a normal battery would have died and been physically replaced 5 separate times, giving scientists an unbroken, continuous record instead of frustrating gaps caused by dead equipment sitting miles underwater. Space missions could shrink their power systems dramatically, freeing up weight and space for scientific instruments instead of bulky batteries and heavy solar panels bolted to the side of a spacecraft. Every single kilogram sent into space costs an enormous amount of money to launch off the ground, so shaving weight off a power system means either dramatically cheaper missions or room for more actual science equipment packed onto the same rocket. Even something as simple as a smoke detector or a medical implant could become something you install once and genuinely forget about for the rest of your entire life. The kind of quiet convenience that sounds small until you actually imagine never again hearing that annoying low battery chirp at 3 in the morning. There is also a bigger competition playing out here between countries racing to control the next generation of energy technology. China has poured billions of yuan into advanced materials research over the past decade, including labs focused specifically on synthetic diamond production and nuclear material engineering, treating this the same way it has treated electric vehicles and solar panels in years past, as a technology worth dominating early rather than scrambling to catch up on later. Winning the race to commercialize small-scale nuclear batteries would give whichever country pulls it off first a serious edge in medical technology, defense equipment, and space exploration. 3 industries that all depend enormously on long-lasting, dependable power sources that do not fail at the wrong moment. That is a pretty big prize, sitting inside a battery smaller than a coin. Defense applications alone could reshape things quietly behind the scenes, since military sensors, remote surveillance equipment, and communication devices placed in hard-to-reach locations would benefit enormously from a power source nobody has to sneak in and replace under risky conditions. But before anyone starts imagining nuclear-powered phones sitting in every single pocket on the planet, there is a much less exciting side of this story that deserves just as much honest attention as everything you just heard. Here is the honest part, and it matters just as much as the exciting parts. That 100 microwatts of power coming from the BV100 is genuinely tiny in the grand scheme of things. Your smartphone needs several watts just to keep its screen lit up for a few minutes, which means the current version of this battery produces somewhere around 10,000 times less power than your phone burns through in a single moment of scrolling. This battery cannot charge your phone, run your laptop, or power your car, no matter how patient you are willing to be. It is built for extremely low-power devices like sensors, medical implants, and tiny chips, not for anything you would immediately recognize as a normal, everyday gadget today. The name never runs out that gets thrown around online is also a little misleading if you take it too literally, because nickel-63 does decay on a fixed, predictable schedule that physicists can calculate precisely. The battery slowly loses power over 50 years. It just does so incredibly slowly compared to a normal battery you would buy at a store. Calling it immortal makes for a catchy headline that spreads fast online, but a more honest description is that it fades so gradually most devices built around it will likely become outdated and get replaced long before the battery itself ever actually gives out completely. Cost is another real hurdle standing directly in the way of this becoming an everyday product. Nickel-63 is not cheap to produce, since it has to be manufactured carefully inside a nuclear reactor rather than simply mined or grown naturally somewhere in the ground. Lab-grown diamond wafers are not cheap either, especially at the size and purity needed for this kind of precise engineering work. Betavolt has not published detailed pricing for the BV100 at any real commercial scale, and mass production numbers that would make this battery affordable for everyday products have not been independently verified by outside experts yet. Until those numbers become public and get tested by people outside the company itself, it is fair to treat the promise of cheap, widespread nuclear batteries as a goal still being actively worked toward, rather than a finished reality sitting on store shelves. Regulatory approval is also a real bottleneck standing in the way, and it is one that gets overlooked a lot in flashy headlines. Any product involving radioactive material, even a very low-level one like nickel-63, has to pass detailed safety reviews in every single country before it can legally be sold there, and those reviews genuinely take real time to complete properly. A hospital in one country cannot simply order a shipment of these batteries overnight and start implanting them into patients the following week. Health regulators need years of careful safety data, long-term studies, and cautious review before anything involving radioactive material placed near the human body gets full approval, and that entire process alone could realistically take much longer than the engineering itself did to develop. There is also the simple reality that Betavolt is a relatively young company, and big claims coming from young companies deserve a healthy amount of patience before anyone treats them as guaranteed, settled fact. Independent labs operating outside China have not yet published their own separate testing confirming every single performance number the company has publicly announced so far. That does not mean the technology is fake or a scam, since the underlying physics of nickel-63 decay and diamond semiconductors is well-established science that has been studied carefully for many, many years already. It just means the leap from a working lab result to a battery actually sitting inside your pacemaker or your home sensor is still a leap that has not fully happened yet, and it is worth staying a little skeptical until independent testing actually confirms it. So here is the real story, stripped completely of the hype that tends to spread fastest online. A Chinese company built a coin-sized battery that uses the slow, steady decay of a radioactive material to generate a tiny but genuinely stable trickle of electricity for decades at a time. And diamond, not the material dreams and engagement rings are made of, but an actual physical semiconductor doing real work, is what makes it survive that long without breaking down under pressure. Scientists absolutely can explain how it works, because the science behind it is decades old and thoroughly well understood, even though building it this small and this safe was the genuinely difficult part that took this long to solve. If this kind of battery keeps improving the way researchers genuinely hope it will, you might one day never think about replacing a pacemaker battery, a deep space sensor, or a hard-to-reach industrial device ever again for the rest of your life. This channel will be tracking every single update on this story as new numbers and independent tests come out over the coming months, so hitting subscribe and turning on notifications means you will catch the next chapter of this story the exact moment it drops, instead of scrolling past it months later after everyone else already knows. Here's a question worth typing an honest answer to in the comments below. If a battery like this one ever became powerful and cheap enough to safely go inside everyday gadgets, which device sitting in your house right now would you want to never charge again?